Alright, welcome back to the channel. Today we have a very interesting question. Your interviewer asks you to implement a binary heap. We'll get into all of this, but first I want to say, if you haven't subscribed to the channel, subscribe to the channel and like this video. My goal is to make this the world's largest resource for software engineering interview questions. That's kind of ambitious, and I know I won't do something as large as, LeetCode or Geeks for Geeks, but I want this to be as helpful and as central of a resource as possible. That's why I give every video a table of contents. That's why I try to keep things structured, so that's like a study resource. Today's question is implement a binary heap. So what is a heap, and how do we implement it? How do we even go about this question? So we're going to get into all of that. So the key thing that a heap offers us is it offers us either the largest or the smallest number of a group of numbers. So we have a group of numbers here in a tree-like structure, and we notice that we have constant time access, or peak. We can peak the smallest element, and it's 5. So this is a min heap. We're going to get into all that, like I said before. But first, I want to say that this is a data structure. A heap is a data structure. A heap is not an abstract data type. The most fundamental things we have in computer science to model the way data is stored and retrieved and worked with is abstract data types. Things like stacks, things like a queue. So if a heap is a data structure and it's not an abstract data type, what is it? So let's investigate the abstract data type priority queue. Okay, so before we investigate what a heap is, we need to see, where does a heap come from? What is a heap an implementation of? So a heap is a maximally efficient implementation of the priority queue abstract data type. Now, what is an abstract data type again? So an abstract data type is a set of behaviors that we define a certain data type to have so that we can even call it that data type. So for a stack, we know we need to support push and pop. For a queue, we know we need to support enqueue and dequeue. So an abstract data type, roughly speaking, is when we support a core API that characterizes that data type, we can then call it that data type, or an implementation of that abstract data type. But the reason it is abstract is because we can do it however we want. They keep it abstract and just say, we want these behaviors, we don't worry about how you're going to do it. So what are priority queues behaviors? So this is roughly how the API goes. So we need to be able to check if the queue is empty. We need to be able to insert an item. The item could just be an object, it could be any type of object we could pass in or something like that, where we can insert it with a priority. We can tack on a priority, and the highest priority item gets precedence for removal. And then we are able to pull the highest priority item. We can pull the item with the highest priority. If I insert items with low priorities and then insert an item with a huge priority, that huge priority item is going to jump in front of the low priority items. So now we're starting to see how this is going to shape how we implement a heap. And then, of course, we can peek an item, so we can just see the item at the top of the priority queue, which is going to be the highest priority item. So now let's look at what a heap is, and let's see the types of heaps we have and how they implement this abstract data type. Okay, so the key thing we need to understand about a heap is that when we're doing a binary heap, it's going to be a complete binary tree. What does complete mean? It's very simple. All we do is we fill the tree starting from here, and then we go from left to right, top to bottom. So I would fill like this, I would fill like that. So for this, do you see how we have the 9, the 8, the 6? We fill like this. We go that, right there, right there, right there, right there. We go from left to right, top to bottom. So if I were to just erase this 2, if I were just to erase that 2, do you see how we're no longer filling from left to right? Do you see how we skip something right here? So then this tree is no longer complete, so we can't do that. If this is going to be a binary heap, we must make sure that this is a complete binary tree. Okay, so we have our min heap here in blue, and then we have this, and then we have our max heap. So the name of the heap tells us the item we will have access to in constant time if we peek. If we do a peek operation, we in constant time will know that 5 is the minimum element of all of these elements in this assortment of items. So for this max heap, our max heap tells us that 9 is going to be the maximum item in this collection of items. So whenever I get a problem that says the largest of something, the smallest of something, I am immediately thinking of using a heap. I'm thinking of using a min or max heap. Now we're going to do plenty of min and max heap problems, but I just want you to become familiar with thinking about these structures for sorting or finding the min or max in a certain set of items. The heap data structure is very useful for that. But today our job is to implement one. And before I go into this, I want to say that the code is in the description. As always, it is very easy to follow the code. You can start with the code, start with this, it does not matter. What we're going to do today is we're going to do insertions and removal on a min heap. So our minimum item is going to be the one at the top. So again, code in the description, but we're going to go straight into a walkthrough with a min heap right now. Okay, so our job is to build a min heap in this empty space, and we have these items to insert. Again, the code is in the description to see how this actually works and what the implementation looks like, but we're going to just walk through the concepts here. What we're going to do is insert the 10. So let's insert the 10. We have nothing here, so we just insert 10. 10 is at the top of the heap. Okay, so now we have inserted 10. Now what we want to do is we want to insert 4. So what we do when we insert an item into a heap is we insert it into the last position. What is the last position? Remember, when we fill our heap, to keep it a complete binary tree, we go from left to right, top to bottom. So we go left to right, we don't have any more room in row 1. So then we go to the next row, which can have 2 nodes. We can branch 2 nodes off of the 10. So we can put an item here. Can I put an item here? Yes, I can. So let's put the new 4 right there. But notice that there's something wrong here. This is not a min heap anymore. We have a 4 here and 10 is greater than it. The item at the top of the heap is not the smallest item. This is not a min heap. What we need to do is restore the heap. When we insert an item, when we remove an item, we're going to do heap restoration operations to restore it. And notice how we do it. I want you to just keep in mind how we do it and what time complexity it's going to entail. We'll talk about complexities later, but let's restore the heap. So what we need to do is we need to take the item we just inserted and we need to bubble it upwards until we have a heap again. So what I do is I say 4. Look at my parent. Parent, are you less than me? We see that the parent is not less than 4. So what we can do is we can swap these items because 4 is going to beat 10 in terms of being small. So 4 is going to get the placement. We're going to swap these nodes. So let's execute the swapping and see where the nodes stand. Okay, so now 4 is finished. We've restored the heap property. We bubbled 4 up while there were parents. We bubbled 4 upwards. So now we have restored the min heap property, as we can see. So now our job is to insert 15. So let's insert 15 into the heap. This is not the final placement. We need to see, can we bubble this item up to restore the min heap property? So 15, let's look at the parent 4. Is 15 less than the parent? Do I beat the parent in placement? So we see that 15 is not less than 4, so we see that 15 is not going to beat its parent. It's going to stay put where it is, and we know that our heap is intact. We know we kept it intact before, and we know we kept it intact after this insertion we just did right now. So that means the heap is intact between all of our operations. What we can do is we can solidify the placement. Okay, so now we have our min heap intact. Our min heap's doing fine. Our smallest item is 4, but what happens when our caller comes along and says they want to remove an item? So how do we remove an item from the heap? First off, I have to give my caller what they want. I'm going to give them their 4. The caller just got their 4, but what item are we going to put in the place of the item that was just removed from the heap from the very top? To keep this a complete binary tree, what is the only choice we have? The only choice we have is the last item in the heap, which is the one that is farthest to the bottom and farthest to the right. So that's going to be 15. 15 is going to go up where we just had the item removed. So let's do that. Okay, so this is where our heap stands. But you see a problem again. 15 should not be sitting right there. So remember what I said before? On insertion, we need to heapify upwards. On removal, we need to restore the heap property going downwards. So the item we just put up here it broke our heap. So what we need to do is we need to look at both children and we need to see which of these children do I need to swap into my position to restore the heap property. And I'm going to keep doing that on the way down. We have this 15. We look at both children. If I do not have a left child, I for sure do not have a right child. Why is that? Because if I don't have a left child, I can't have a right child because this is a complete binary tree. It's a complete binary tree. What we're going to do is we're going to compare 15 against the smaller of the children, because what I want is 15 says, my children, I want the smallest of you to take my place. If I am smaller than you, then you cannot take my place. But if you do beat me, smaller of both of my children, the smaller item of both of my children, if you beat me, take my place. So all we have is 10. We don't have two children, we just have 10 to compare against. So what we're going to do is we're going to see, does 10 beat 15? Is 10 less than 15? We see that 10 does beat 15. So we're going to bubble 15 down by swapping 15 and 10. So let's swap 15 and 10. Now, is this a min heap? Are we done? 15, compare it against both of the children. There's no more children to compare against. We can't bubble 15 down any further, and 15 is in the correct place. We solidify the placement. Okay, so now our caller comes along, and now we have some more insertions to do. Remember, when we want to insert an item, we insert it into the last position, which is farthest bottom, farthest to the right. Insert a 20. Let's insert the 20. So let's see. What we need to do is restore the heap. We look at our parent. Parent, am I smaller than you? 20. Am I smaller than 10? 20 is not smaller than 10. 20 will not beat its parent, 20 will stay where it is, and our heap is intact. Okay, so now we need to insert 0. Where do we insert 0? We insert it into the final position. Well, we're going to go down and to the right. So no more room here, no more room here, going to the right. Now we need to go to the third row. Now, the farthest left we go is here, and yeah, we can insert the 0 there. Let's do that. So we've inserted the 0, but we don't know if the 0 stays there. And we can tell the 0 is the smallest item. It's going to bubble all the way up. But let's see what happens. Let's see how we bubble this thing up. 0 asks its parent, 15, am I smaller than you? Yes, 0 is smaller than 15. Do a swap. Okay, now 0 asks its new parent, 10, my new parent, 10, am I smaller than you? And then 0 realizes it's smaller than its parent. So we swap 0 and its parent. So let's swap them. Okay, so do you see how we just bubbled up the item we just inserted? This is how insertion works in a heap. We put it into the final position, whatever that may be, going bottom and then farthest to the right, and then we bubble it up against its parents. 0 is at the top of the heap, and we have restored the heap. So we can solidify the positionings now. Okay, so now what we want to do is insert 30. So again, we're going to insert in the last position. Go all the way down as far as we can. We end up in this row. Go far right. The farthest right we can go is right there. So we insert the 30 there. 30 is going to ask its parent, 10, am I smaller than you? We see that 30 is definitely bigger than 10, so 30 will not bubble up. So what we're going to do is solidify the placement, and we can't bubble 30 up. We still have a min heap, and everything's fine. Okay, so now a caller comes along, and they want to remove the smallest item. They perform that operation, and that's fine. And what we need to do is we need to take the last item in the heap, and we need to put it at the top. The last item is 30. Now, 30 is at the top of the heap. So what we need to do is we need to bubble it down, and now we have the ability to compare against children, and I need you to pay attention, this is critical. 30 looks at both of its children, 10 and 20. We want to put the smaller of the children in 30's position. Why? It's a min heap. We want the smallest items to bubble upwards. So the smaller item is 10. So does the smaller item beat 30? 10 is less than 30. 10 beats 30. So what we do is we swap the smaller item of the two children with 30. So we swap 30 and 10. Okay, and now we're still sitting at the 30. So what we need to do is 30 needs to look at both of its children. The smaller of my two children. We're missing one child here, but that's fine. 15 and nothing. Which is smaller? 15 is smaller. So does 15 beat 30? Is 15 less than 30? Yes, 15 does beat 30. 15 needs to be higher in the heap because it's less, and this is a min heap. So we swap 30 and 15. So I want you to notice something. Do you see how the farthest we can swap downwards or upwards is the height of the tree? So do you see why the complexity of insertion and removal from a binary heap is going to be log of n? The thing is, we're going to have roughly log n levels. We're going to do logarithmic work, traversing, in the worst case, if we go all the way down and we traverse all of the levels. That is our upper bound for the time we could spend inserting an item where we need to bubble up, or removing an item where we need to bubble down like we just did. As we can see, this is a min heap, so let's solidify our placements again. And that was a removal operation. So what we can do is we can do another removal operation. So let's remove the 10. The caller wants to remove the smallest item, let's do that. And what item goes into 10's place? The last item in the heap. It's not really last because this is a binary structure, but the last item is 30 because this is a complete tree. So let's put 30 into 10's place. So now this should be pretty rapid. We compare the two children. Which is smaller? 15. Does 15 beat 30? Yes, it does. So we swap them. So we swap 30 and 15. Okay, so we've done two removals. So let's insert a 2. So let's insert a 2. So we insert a 2. What we do is we ask our parent, parent, am I less than you? Yes, 2 is less than 30. Do a swap. 2 asks its parent, again, parent, am I less than you? Yes, 2 is less than 15. Do a swap. Okay, so there's no more parents to check, so 2 is now in its right place. And do you see how we bubble up the minimum item? After insertion, we still have a min heap. So now we're completed 2. So now let's insert 4. So let's insert 4. And you see how we inserted it into the last position? So now 4 sees. 4, am I less than my parent? 15. Yes, swap. And then 4 asks its parent, parent, am I less than you? Is 4 less than 2? No, 4 is not less than 2. 4 stops in its tracks. And it stops there, and we have restored our heap. So now let's insert -1. Where would we insert -1? We'll insert it here, because this needs to stay a complete tree. Okay, -1 we know is going to bubble to the top. We can see that. But what -1 will do is ask its parent, 20, which is less? -1. So we do a swap. So, -1 versus its parent, 2, which is smaller. -1, swap -1 and 2. So the key to this is we want to restore a heap. When we insert an item, we want to bubble it up. When we remove an item, we want to bubble down the last item that we just placed in the removed place. So this is all it is. This is the essence of removing and inserting from a binary heap. Insert -3 finally. So we insert -3. The last place we can put it is right there. We insert -3. -3. Am I less than my parent? Yes. -3 is less than 2. Do a swap. -3 and -1. -3 is less than -1. It's less than its parent. So do a swap. Okay, so now this is the final state of our heap after all of these operations. And do you see how with a heap, we see that going downwards, we slowly get greater in value. Or you can see it the other way, going bottom to the top, we see we slowly get lesser in value because this is a min heap. This is what a heap is about. This is what a binary heap is about. It is all about keeping these quantities in a gradually decreasing or increasing order in this structure and having constant time access to the smallest item. It's not constant time removal. Removal is going to entail logarithmic work because we're going to do a traversal of the height at worst case for insertion and removal. I'm saying constant time peaking. If we just look at the item, we instantly will know what it is. So that's what a heap is all about. The complexities are going to look like this. So the time complexity for the insertion, as we saw, is we'll put an item in the last position, then at worst, we're going to bubble it up the height of the tree. So that's why it's logarithmic in nature, because we can express the height of the tree as a log of the number of nodes. If you haven't seen my video on logarithms, it's very important to watch that because it's great to have an intuitive understanding of this. Removal is going to entail, at worst, we're going to upper bound that with logarithmic work, log of n, because if we remove an item, that -3, and then we put the last item in its place, what we're going to have to do is we're going to have to bubble this item down. 2 is not the smallest item in this heap. We know it's going to be -1. This is going to entail, at worst, we might bubble the 2 all the way back down. So again, we might do logarithmic work, and that's how we express it, because we can express the height in a logarithmic fashion. And again, I have that video on logarithms. I think it's very important to watch because it's something that confused me a lot when I was learning it. That is all for this video. If you like this video, hit the like button, subscribe to the channel. My goal is to make this the best channel for software engineering interviews with clear explanations and very intuitive understandings of these problems that are often made to be harder than they really are. So that is all for this video, and